Hi guys, I'm back. All right, let's move on to the next one, which is muscle. Let's see. Okay, share screen. And that's this one here. Sure. All right. So today we're going to talk about the skeletal muscle. And this is um, the extension from uh, the electrophysiology that we talk about, that cell has memory potential, and some cells can be excited. So skeletal muscle is one of it. It can be excited. What does it mean be excited? It means that these cells can generate action potential. So not all cells can generate action potential. Only 3 types of cells can generate action potential. Muscle cells, okay, include skeletal muscle, cardiomyocytes, and smooth muscle, nerve cells, and secretory cells, those endocrine cells. All right, so skeletal muscle. Today in this chapter, we will learn about the structure of the muscle. In your anatomy, you probably know the structure of the muscle already. So today we are going to talk about some more physiological aspects of those structure. How much did you learn from the anatomy? Did you guys have to memorize all these different names of each, like muscle organ, like biceps, triceps, deltoid, etc., like 300 something of all this? Uh, I don't know. I mean, today we are not going to talk about, you don't need to worry about like memorize all the 3. I don't even remember my kids' grades. Yeah, but if you work on this one, you need to memorize those. All right, um, so we don't need to worry about each like different muscle organ, but we need to know the general physiology of it. Neuromuscular junction, that is the connection of nerve and the muscle. Contraction, how muscle contract, and also function of the muscle cells. All right, ready? Let's go. So in our body, we have 3 types of muscle: skeletal muscle, cardiomyocyte, cardiac muscle, and the smooth muscle. So the one that you can move around, those are the skeletal muscle. And cardiac muscle is the one in the heart. You cannot control your heartbeat. Okay, so it's not voluntary. It's not skeletal muscle. And smooth muscle are those cause the contraction in your vessel, like your blood vessel, your GI tracts. Those contractions are not controlled by our intention. Those are local response to move the things moving forward, and also controlled by autonomic nervous system. So even though that they are different muscle, they are something that you must know is that skeletal muscle and the cardiac muscle are all striated muscle, that they have this striated appearance. So this is skeletal muscle. So if you still remember your anatomy, I actually don't know what you guys learned in anatomy, but in my anatomy, I need to memorize all this muscle and the bones. So so in the anatomy that we learn different like muscle organ, right? Each of this piece. So each organ, each muscle has its tendon to connect to a bone, and so each of these muscle organ is wrapped around a membrane. This membrane is called epimyosin, and that kind of like separate it from other muscle. And also other part of the body, so there will be no damage to the cells. Okay, there's some like connective tissue to protect, like skin of the muscle organ. Okay, is to protect it. It's called my epimyosin. Now, inside of this muscle organ, if we tear it apart, we can see a lot of like fascicles. Okay, this is called fascicles. And in each fascicle, this bundle of muscle fibers, in each fascicle is wrapped around another membrane. This is called perimyosin. Okay, and then inside of these fascicles, we will have hundreds to thousands of cells. Those are the muscle cells. Each muscle fiber is one muscle cell. And that cell is also further protected by another membrane. It's called endomyosin. So endomyosin surrounds individual muscle fibers. So each one muscle fiber is one cell. So that cell has very elongated shape. All right, so this thing is a muscle cell. It's a muscle fiber. One fiber is a cell. So this one. So here, surrounding it has, outside has this endomyosin, like connective tissue to protect it. But each cell is also encapsulated by a cell membrane. That's like every other cells. They have cell membrane. In the muscle cells, it's something. Here we have the cell membrane. Let me see. It's right here. That's the one. Do we have name here? Yes. So cell membrane in the muscle has a special term. It's called sarcolemma. Sarcolemma. It's right here. Sarcolemma. So that is the membrane of its cell membrane. It's plasma membrane. But in the muscle cells, they come with different terms. It's called sarcolemma. And so cell has also, if you remember a cell, okay, let me draw it here. If you remember a cell, right? Cell has cell membrane. That's the same thing here. Sarcolemma and plasma membrane. What else do we have in a cell? Nucleus, right? Most of a cell has a nucleus. Nucleus contains the DNA, the chromosome. In muscle, where is the nucleus? Nucleus right here, right here. That's the nucleus. That is the nucleus. So muscle has many nuclei. Okay, their nucleus are pushed just underneath the cell membrane. So their nucleus are moved here. And they are not just one, they have several underneath the cell membrane. Okay, so that's their nucleus. What else do we have in the cell? We have mitochondria, right? We have mitochondria. Where is the mitochondria in the muscle? Right here, we have a lot of mitochondria. This is important. What's the function of mitochondria? To produce ATP, right? So here, that's the one here. This is mitochondria. Mitochondria here. Here we can see a lot of mitochondria. Okay, what else do we have in the cell? So cell, let me make it just one nucleus. Okay, so say just so this is mitochondria right here. Okay, and let's say we have the nucleus. So what else do we have? We have the nucleus here. Here we contain DNA. Okay, and what else do we have in the cell? We have ER, right? Endoplasmic reticulum. We have ER, ER. I don't wanna. I don't want. Maybe that's why. All right. ER, endoplasmic reticulum. Yeah, we do have ER somewhere. That's right here. Yeah. So right here, this blue thing is ER. It's called sarcoplasmic reticulum. So this is ER here. Nucleus, sorry, nucleus. Nucleus is nucleus is here. Okay, ER is here. It's called sarcoplasmic reticulum. What else do we have in the cell? We have the inside of cell. We have membranous organelles. So these are all membranous organelles. We also have non-membranous organelles, which include the ribosome. Ribosome usually is located attached to the ER. It's called rough ER. We also have cytoskeleton, right? We have the cytoskeleton in the cell. Cytoskeleton, okay? And cytoskeleton, 3 types. In the muscle, these are cytoskeleton. These fibers are the cytoskeleton. So in the cell, our cytoskeleton basically is wrapped around, field to make the structure, like scaffold of the cell. In the muscle, the cytoskeleton are aligned. What are the cytoskeleton? We have 3 types of cytoskeleton. Right? And the large one is microtubule, intermediate filaments, and the microfilament. The microfilament is composed of what? Actin. That's here. That's these fibers, is actin. So we will learn that. So basically this whole thing. So this one is a thin filament. This thin filament is this cytoskeleton. So we have the cytoskeleton here. Okay, cytoskeleton. Okay. So this, okay. What? This thin filament. All right. This thin filament is this cytoskeleton. So we have everything in one-on-one match to each other. The cell organelles in the cells we all have it in the muscle cells. And so that the whole thing, this one fiber is a cell. It's one cell. So what's important in the cell is the this myofibril. So if we look at this one here, each one of these is called myofibril. Myofibril is a bundle of cytoskeleton, as you can see here, it's a cytoskeleton. And the myofibril is the one that provides muscle contraction. So let's look at the myofibril. So this is the myofibril. And in the myofibril, we have several things that you need to able to recognize. Those are the two major things is thin filament and the thick filament. So we have the thin filament right here and the thick filament right here. So we have two type of filaments. interlaced to each other, okay? And these thin filaments are all attached to Z line. So this one is called Z line. That's how we organize all these filaments in a very organized way. Everyone is aligned with the Z line, okay? And then thick filament is attached to this M line. This is an M line, thick filament. So we have thin filament, thick filament attached to the Z line, thick filaments attached to the M line, and they are all like interlaced to each other. What's more important here is that, in addition to this, is that these thick filaments have this. This is like a little spine here. These are called the myosin head. So this is made of myosin. And this myosin head, this one is myosin head. That myosin head interacts with the thin filament. Thin filament is made of actin. This is one of the cytoskeleton. Actin. And so that's how they interact. We will later talk about how they interact and how their interaction could provide the muscle force. All right, with this one here, there are some other things you need to know, which is that when the location that the entire Z line to Z line, this is a unit of like muscle length. This one is called a sarcomere. Sarcomere is Z to Z. So that range, that distance, that region is called a sarcomere. And inside of this sarcomere, we can kind of like separate into different bands. When we have the location that only showing thin filament without thick filament, this is a region that's only, very purely just one type of the filament, only thin filament. This one is called I band. I refer to the isotropic, means that it only has one type. So it only has, whenever you see it, the thing is surrounding it. So when you see it from different angle, they will be transparent no matter what. There will be no block of the light. So it will cause this light appearance of this striated muscle right here. So right here, so that this is the I band, sorry. So this will be the I band, that region, this one here. So this will be the I band. This will be the I band. Okay, this light area, this transparent area is the light band. And next to light band is the dark band. Okay, this is also called A band. A is called anisotropic. It's also called a dark band. And A is where we have the overlap of thin filament and thick filament. This A band though, I band can be shortened. If they contract, this 2Z line will come closer and everything will filled with the thick filament, everything. So everything will be filled with thick filaments. Everything will become the A band. Only when they are separated, the I band will show up. And inside of it, when it's open, we will also have a region that only has thick filaments without thin filament. And this region is called an edge band. So that's the thing you need to memorize. Z line, I band, A band, H band, Z line, M line. M is a middle line. Z line is zigzag that attached to the thin filament. M line is one attached to the thick filament. Those are quiz questions, okay? M line attached to what? Thick filament. Z line attached to what? Thin filament. What's I band? Where we only see the thin filament. What's the A band? A is anisotropic, means that when we see it from different angle, we may see the overlap of two filaments, or we only see one. So, and that will appear to be dark in the muscle, dark band in the muscle, and that's the overlap of thin and thick filaments. Then what's the edge band? Edge band is only has these thick filaments. So with this one in mind, let's see how these two interact, thin filament and the thick filaments. So this thing is called myofibril. The way it interacts is that the thick filament has this myosin. So a thick filament is composed of this myosin. Myosin has this myosin head, and the myosin head would interact with thin filaments. So the myosin head will have to attach to that. When they attach to it, anchor on it, and then move. So it's like a rolling a boat, and so you keep rolling it. This boat will moving forward, and this thin filament will moving down to this direction. So basically that we have all this pedal to swing in the same speed or the same direction. And this pedal is this myosin head. Myosin head attached to the thin filament, and roll it, and pedal on it, attach on it, and roll it. And by doing so, we have this sarcomere become shorter, and that's how we make the movement. How do we control the muscle? To allow it, and on the other hand, we have this thin filament. The thin filament has three components. One is the actin. Actin is this little bit. So this is the monomer. They form this polymer, this fiber. And we also have troponin and the tropomyosin. We will need to learn about this structure. And then we will know that how myosin had attached to the thin filament. So this is the thick filament, the thick myofilament, the thick filament. This thick filament is composed of the myosin. This is one myosin molecule. This myosin molecule is a protein. So this one is a protein. This is a protein. A protein. Remember that proteins have like a folded structure. So same thing here. This protein has folded structure. So we have this, you can see that here we have one tail and two tails. These two tails wrapped together. We have two tails. Here we have, and that they wrapped around and also form this head. This is tail. This is the head. and head is where we have the interaction of myosin and actin. I want you to focus, pay attention on this side. On the head, we have two binding sites. One is the actin binding site. The other one is the ATP site, ATPase site. So we will know that this is a site. Myosin would interact with actin. And this is a site that it will use ATP as the source of the energy. So this myosin head will act with the actin by binding the actin with the actin binding site of the myosin head. All right, so that's the myosin. Let's look at the actin, thin filaments. Thin filaments has three components, as I mentioned before. This is the thin filament right here. This is the thin filament. If we zoom in, we can see three components here. We have the actin. This is actin. This form this cytoskeleton. We also have troponin, and the troponin here, troponin, and the tropomyosin. Now, as we already know that myosin head want to interact with actin because the nature like a tendency of the myosin is to have this actin binding site to bind on actin. So they want to do that. Myosin head, we want to bind with actin. However, actin would not get bound unless the time is right, right? So our muscle will not contract just randomly. Our muscle contract when we want it to contract. So even though the myosin head is ready, you know, desired, have this desire to bind with actin on this actin binding site. But if time is not right, actin will not be ready. And how do actin prevent? How do the thin filament prevent its actin to be bound by the myosin? The way it does is that it blocks it. So here is the actin, right? Actin is one that like a very precious bits right here. And the myosin head is right here. Let me draw myosin head, right? So, okay, have this, this is head. They want to bind with actin, okay? It's all very excited, everything ready. I want to bind you, okay? You want to, you know, get on you. But time's not right. You should not let the muscle like randomly contract to each other, right? So the way we do this is that we have this myosin, tropomyosin. Tropomyosin is like a cloth or a band to cover the actin. You can see that it cover what? It cover on the actin. We have this myosin binding site. So it's like a key and a lock, right? So here is a key, here is a key, here is a lock. Or it's like, to me, it's very much like a kiss, right? Like a myosin head want to kiss it and the kiss on the myosin binding site. Okay, so it's blocked by the tropomyosin. So when the time is not right, it's not going to happen. And the way it does is that the tropomyosin block it. So this is, in this condition, this is called relaxed. Means that muscle is not contract. It's all relaxed. It's all relaxed. Myosin has ready, actin is blocked, so nothing happened. They don't see each other. All right, now what can we do when the time's right? When the time is right, our brain will tell the muscle, okay, contract. What it does is that it will inject calcium into the cell. And so here is the muscle cell. It will open up. Calcium channel, and the calcium will go in. Calcium will go in. When calcium go in, means that it's time to do it. You know, it's time to contract. What calcium will do is that calcium will act on the troponin here. Calcium will bind on the troponin. And then, because this troponin is the handle to move the tropomyosin. So this one is like a door, right? Open the door. You want to open the door, you need to do the handle, right? You need to bend the handle and push it to open the door, all right? So calcium is very much like the one to like bend the handle. So troponin is the handle. Then it got bended. Open the door, all right? The door is now open. Then tropomyosin see the actin binding site. Actin binding site see the myosin binding site on the actin. So on the actin, we have the myosin binding site. On the myosin head, we have the actin binding site. So they are meant to be together. And now door is open. They see each other. They will just bind on each other. And that's how these two can interact with each other. So the key here is that calcium. We need to have calcium. Calcium binds on what? Troponin. Okay, calcium binds on troponin. And what blocks the actin from seeing the myosin? Tropomyosin. Yeah, tropomyosin. Okay, and when the calcium binds on it, troponin is like a handle. Open the door. The tropomyosin is moved away. Now actin and the myosin see each other. They are meant to be. Actin has the myosin binding site. That's in its gene. Myosin has its actin binding site. It's also, that's what it's born for. And then these two just act on each other. And then that can cause the contraction. Clear? All right. All right. So so that's the how muscle and actin binds with each other. Now let's talk about the next step is the neuromuscular junction. So the nerve need to get excited. Muscle need to get excited in order to conduct that contraction. So the nerve coming from the excitement coming from the nerve. So muscle is a thing that it can generate, say, action potential. The stimulus coming from the nerve. So we have the nerve. So one nerve, one motor neuron. Where is my pen? So this is the spinal cord. Spinal cord, spinal cord. So in the spinal cord, we have this motor neuron, and the motor neuron will then send axon to our muscle. Send axon to our muscle right here. So this one neuron will send axon. That means that we will talk about the nerve. So let's just make it easier. This one here, just think that there's nerve, and the nerve has the extension. I think we talked about the nerve, and this extension is called the axon, and that axon will then interact with muscle here. Okay, so this one is nerve. N-E-R-V-E, nerve. This is also called one neuron, because this neuron is for motor, so this one is called motor neuron. This motor neuron is not the motor neuron in the brain. This one is motor neuron in the spinal cord. So it's also called lower motor neuron. So in the brain, it's right here in the brain. And here we have the motor neuron. This one is one that we directly control in the brain. So this one is called upper motor neuron. So upper motor neuron, when we decide to say grab that bottle, right? To grab that bottle. When you want to grab that bottle, you send signal, grab that bottle. Very easy, just one command. But that movement need to be conducted by so many steps and a different sequence, right? You have so many different muscles. You want to grab a bottle, there are so many different movements need to be considered. Who comes first, who comes second? So that detailed process is not really by your thinking. You are not care about that details, right? Those detail is already programmed in your spinal cord. So you say, let's walk out. You thought, let's walk out. And you start to walk out. But by walking out, there are so many muscles need to be considered. And but you don't really program that in the brain, right? Because you don't really care about that details. And that basically is a repeat process that we do it like every time. Grab a bottle is a command. It's not like we do it every day, but when you grab it, the process is very much the same. When you walk out, say let's walk out. When you start to walk, the process is very much the same. So that repetitive process is something that you don't need to reprogram it. You don't need to reinvent it. Something that's, you reinvented it the first time. Like your baby, you start to walk. You start to program train your nerve to walk with good balance. But once you do it many, many times, your body memorize it, program it, making a circuit where? In your spinal cord. So it's right here in the spinal cord. So spinal cord that works, do that like a sequential individual muscle control. Your brain only provide the command. Your detailed process is done by your spinal cord. Now, spinal cord this command will send signal to the lower motor neuron, then lower motor neuron will control muscle. Each motor neuron has the axon to control several muscle fibers. So one nerve, one motor neuron can control a group of muscle. So when some nerve control large group of muscle, some nerve only control small group muscle. So there are good and the pro and the cons in each case. That if one nerve control a lot of muscle, then that command can just one single calling or one single command, one single electric signal can cause a lot of muscle to be contracted and provide a force, to provide a large force. But with that one, you don't have the detail. You don't have the precision of the movement. On the other hand, if the one neuron only control a small amount of muscle, then you don't have large force, but you have the precision. And that group of the muscle is called a motor unit. So that's a motor unit here. Now, when the nerve innervate into the muscle, this is how they interact. This one is called the neuromuscular junction. That nerve innervate to a muscle. So we have this one. This one is nerve. This one is the muscle. And one thing you need to know is that they do not physically attach to each other. There is a gap. So there is a space. This space is called synapses. It's not shown here, but that's okay. Don't worry about that. So it's not connected. And so how do they communicate if it's not connected? Here we have the nerve. Nerve will send out an action potential. Action potential will travel from the nerve into the, into the axon terminal. That action potential will travel all the way down here. When it's down here, because it's not connected, electric signal has to be connected in order to be delivered. But it's not connected. What can we do then? So what we do is that when the action potential travel down here to the, this one is called an axon terminal. Axon terminal. When it's reaching the axon terminal, then it will cause a release. It will cause a release of several particles released from the nerve. So here we will have a lot of several particles to be released from the nerve end. And that particle will travel, will diffuse from the nerve end to the other side. And that's how these two communicate to each other. Action potential is electron signal. It cannot move across that gap junction, that gap is not connected. So the signal got to be delivered. It's not delivered directly by the electric signal. It's delivered by the chemical, by these particles. This particle has a name. It's called neurotransmitter. Neurotransmitter. So the nerve, the action potential travel down to the axon terminal, will then trigger this nerve end to release particles. This particle is a neurotransmitter. In our body, we have about 50 kinds of neurotransmitter. So there are many different kinds. A very typical one is acetylcholine right here. This one is the neurotransmitter that's important for muscle contraction. Other one like dopamine is also neurotransmitter in the brain. A very common one is called serotonin. Yeah, serotonin and the dopamine are neurotransmitter in the brain, and these two are important to relate, to trigger the circuits that control, that provide our emotional influence. So for people who has depression, etc., or some like mental like a issue, then this neurotransmitter may be affected. It's probably caused by or related to this, the increase or decrease of these neurotransmitters. So in our body, we have so many different type of neurotransmitter. Other neurotransmitter like norepinephrine. This one is important to boost our alertness. So in the neuromuscular junction, the neurotransmitter is acetylcholine. It's right here, acetylcholine. So this one is also a quiz question. Which is the neurotransmitter for the neuromuscular junction? So you may see norepinephrine, serotonin, dopamine, acetylcholine. Which one? Acetylcholine, okay? Acetylcholine. So when it's released, it acts on the muscle, acts on this acetylcholine receptor. Acetylcholine receptor is a type of receptor that will open a sodium. So here is the acetylcholine receptor like. So acetylcholine receptor is very much like a channel. And here is the receptor. So when the acetylcholine binds on it, this one will open and will allow sodium to go through. And when the sodium channel, so this one is it's a ligand gated. Sodium channel. This ligand or ligand is the acetylcholine. So when it binds it, it opens, sodiums can go in. Do you guys remember that in the cell, do we have more sodium outside or sodium inside? Outside or inside? Outside, that's right. We have more sodium outside. And so when the sodium channel open, the sodium will diffuse in. And that sodium diffuse in will make the memory potential to become positive or negative. So before sodium goes in, will memory potential to be negative or positive? So before it's negative, right? Because inside of cell is always negative. Now when the sodium goes in, is sodium positive or negative charged? Sodium is positive, so it will make the memory potential to be positive. So here is the original membrane potential is about negative 70 millivolt, and sodiums go in, will make it a little bit positive. When it's above this threshold, then it will trigger an action potential. Let's use another color. It will trigger an action potential. And here, trigger an action potential. And so that's how we activate the nerve. That's how we stimulate. Of course, you know, sometimes you may, if you want, you can use electrode to energize the person by just directly applying an electrode. But the way we control our muscle is not really electrolyze it. The way we do it is use our brain, right? We control the muscle movement by the brain. So it's very precisely controlled movement. You need to be very grateful that you can have all these movements and very smoothly and do it as you want it. Because a lot of things can go wrong in all this process. Really, our function, our body function is so complicated, and a single mistake can really make all this process to be very bad. So be grateful, you know, all the time. Be grateful that you can still be able to move and do what you want to do. Okay. All right, so that's this one here. Let me summarize it again. We have the brain send out signal to the nerve end. Action potential will cause the nerve ending to release neurotransmitter. This neurotransmitter is called acetylcholine. So that's one quick question, which neurotransmitter? And then acetylcholine will act on the receptor. This receptor is a ligand-gated sodium channel. So when acetylcholine binds on it, it opens up a sodium channel and the sodium go in. Sodium go in will make the muscle memory potential to be increased. When muscle memory potential to be increased, it will trigger action potential. And then muscle will be excited. Okay. So here is the receptor. This is the ligand-gated sodium channel. You can see that acetylcholine binds on it. It opens up, sodium go in. This receptor also has a name. So this name is also important, a quiz question. Where's my pen? Right. It's called a nicotinic acetylcholine receptor. Okay. It's because that it can be opened by acetylcholine. That's the physiological function. However, nicotine, smoke, nicotine, can also activate it. So that's why it's called nicotinic acetylcholine receptor. So this one is the whole process, the happy time that your nerve excites your muscle. You have the action potential, choo, choo, down to the axon terminal. When it reaches, so here is action potential, choo, choo, down to the axon terminal. Here is your action potential, right? Down to the axon terminal, so action potential right here. When action potential reach, it will cause the neurotransmitter to be released. The way it does is that it will activate, it will opens up, this action potential will opens up a calcium channel. And the calcium channel, because here we have these vesicles, because these neurotransmitters are protein. Remember how protein is synthesized from the cell? Okay, let me draw here. This is the nucleus. We have the DNA, right? And the DNA will release, will have the RNA. RNA will go into the go to the ER with the ribosome to produce the DNA. DNA will first form in the vesicles. Then these vesicles contains DNA. And then it will go to the Golgi to get further packed, right? To get it further packed, contain DNA, further packed, batch out. So here is a lot of vesicles contains this protein. Now, that's the cell. And when they are not going to be released just randomly. So action potential travel here, action potential travels down here. And these vesicles are, when you have all these vesicles contains the neurotransmitter, it's very much like a boat docking and ready to be shipped. So here is the docking area, and you have all these boats, right? Boats here, boats here, boats here, boats here, to be ready to be shipped, to be moved out. And the signal is calcium. So when action potential travel down here, it will open the calcium channel. Then calcium will make this bolt to, can I just move one bolt? No, all right. We'll make one of the bolt, make the calcium. Calcium 2 plus will come in here and make the bolt to be released from ducting. The UCK or DOCK, ducting. You know what I mean. So they will be released, and then the vesicles will be released, and then the neurotransmitter will be released. All right, so that's 1 and 2, calcium coming in. These vesicles was already sit there and ready for a signal. Calcium coming in, unducting, then unduct them. Then this vesicle will move to the end, release what they have, dump all this into the ocean in a way, and then they will diffuse. When they diffuse, they will be received by the nicotinic acetylcholine receptor, and they will allow sodium to go in, okay, because this is sodium gated channel. So 3 and 4 binds on it, opens up, sodium going in. When sodium going in, it will bring the memory potential to become a little bit positive, right? Like here, right? And then it will trigger an action potential. Now, action potential has a depolarization and a repolarization. What's the channel open for depolarization? Sodium channel, that's right. So it will trigger here a sodium channel, voltage gated, because this sodium channel is not ligand, like this one here is a ligand gated, meaning that it's opened by a ligand. This ligand is acetylcholine. The depolarization is derived, is achieved by a open of sodium channel, and this sodium channel is voltage gated because it senses that memory potential is different now. It's different this time. I received because memory potential is above the threshold, and that memory potential is a voltage. So it opens up the sodium channel, and then we have the action potential. So that is 3, 4, 5 opens up, and the threshold 7, 6, 7, 6 right here. So opens up sodium channel, and then we have the action potential, and we have the action potential right here. That will propagate, and then our entire muscle will get excited. It's only from one single location and spread. Your muscle will contract. So this one is nerve. One nerve sends out several nerve ending axon terminal, and the whole muscle, this group muscle are called a motor unit. And so one nerve action potential can excite multiple muscles. Excuse me. So this one showing you some more detail about that. Here, action potential travel down to the axon terminal, release ACH. ACH is the acetylcholine released. Then it opens up the sodium channel more. A little bit potassium leaking out, but the majority is the sodium. And this one generates action potential. We have the depolarization, the sodium repolarization. So this one is actually the combination of, this one is not clear, but we have the action potential, depolarization, repolarization, action potential will then travel in this one is the muscle. In the muscle though, muscle is thick. As you already know that it has several fiber, what do we call it? Myofibril, sorry, myofibril. Myofibril. And so the way that action potential only travel in the cell membrane. So that's the cell membrane, right? Cell membrane. Move it back. Come on back. All right. So it's the cell membrane. Action potential only travel in the cell membrane, so it may not affect anything inside of it. So the way that our muscle does this is that we have something called T-tubule. So what it does is that this membrane, okay, let's just remove all this. This membrane extend to the cell, like this one. Okay, this one here. Like this one here. So that's the cell membrane. So the cell membrane action potential will then now have this kind of like a wheel to travel. They travel on the surface and then go with the surface down to this one. It's called T-tubule. So that's the T-tubule right here. Down to the tip of the muscle cells, and then that can bring the action potential to the center, to the heart, to the inner portion of each cells. And when they travel down to here, they will remember that that's what we really need for actin and the myosin to interact is the calcium, right? So we need to have calcium coming here. We need to have calcium. Where is this calcium coming from? Now we have the action potential, muscle are excited, action potential travel down to the T-tubule. So muscle are excited, but where is the calcium? We need calcium, otherwise we cannot complete this action. Now, calcium is stored in a place called the sarcoplasmic reticulum right here. So this one is equivalent to endoplasmic reticulum in regular cells. So it's an ER. In regular cells. Just in the muscle, it's called sarcoplasmic reticulum. And then here, in other cell, in typical cells, it contains some calcium, but it's not that critical. However, in the skeletal muscle, this calcium is important because no calcium, no contraction. And so that action potential travel down to a T-tubule. T-tubule will then have this wire connect with the sarcoplasmic reticulum. This action potential will then opens up this door. Action potential down here, activate this DHP receptor. You don't need to memorize this, but you need to memorize that calcium is stored where? Endoplasmic reticulum, because we already learned this term. Then where? Sarcoplasmic reticulum. Then calcium coming out. And then it can do its work. Calcium binds on what? Troponin. That's right, troponin, okay. Bind on troponin. And then troponin is handled, and you need to open the door. Tropomyosin will be moved away, and myosin has seen the actin. That's what it has been waiting for, and then we have the muscle contraction. So here is a quiz question that T-tubule That's a new term we learned in this one, T-tubule. T-tubule is an extension of what? Cell membrane, okay? So T-tubule is a muscle membrane, sarcolemma in the muscle, or just plasma membrane or cell membrane. It's the same thing. It's an extension of it, okay? And so here we have two quiz questions. T-tubule is an extension of what? Cell membrane, okay? Plasma membrane. And where do we store, where does the skeletal muscle store the calcium? Sarcoplasmic reticulum, okay? So that's the two quiz questions down there. So here is the action that we already talked about. So 1, 2, ACH is a choline binds on the receptor, nicotinic receptor, nicotinic is a choline receptor, sodium coming in, and then trigger an action potential, travel to the T-tubule, that is it. In the T-tubule, then activate the DHP. DHP, you don't need to memorize it because we actually didn't talk about what DHP is for. Then but memorize it if you want. You know, it's not like don't. It's good to memorize it, right? It's a good thing. So don't get discouraged by me. Yes, good, memorize it. Okay. All right, so then DHP has this wire connect with sarcoplasmic reticulum, open the door, then calcium coming out, calcium binds on the troponin, and then myosin head bind with actin, tropomyosin is removed, and then we have the interact, right? Now we have the interact. And now the myosin head, like rolling a boat. That rolling a boat requires energy though. Do we talk about that energy? Yes. So that rolling a boat require energy. So this myosin head attach. Attach doesn't mean it move, right? So everything is attached. Now it's time to move. This move require ATP, require energy. This one is called power stroke. It's a move myosin head. It's also called cross bridge. It's equal to myosin head. This is equal to the myosin head. Okay. That attached to the actin, and now it's moving. The moving require ATP. So it move, attach, move, then attach, move, then attach, move, and then release, then attach, move, then release. So that's 4 steps, and from the beginning to the end. So basically, it has to be tilt, attach, move, release. So 4 steps, right? Because you have to have myosin head to tilt, got energized, attach. When calcium's there, move, right? And then detach. So 4 steps. And that movement require ATP. So this one require ATP, troponin, myosin head. Troponin binds the what? Calcium, that's right. Calcium binds on it, remove this tropomyosin. Tropomyosin is a door, block these two to see each other. And the tropomyosin blocks the binding site on the actin, move away, then binds on it. Same thing here, but this one kind of complete it. So calcium is moving from where? Sarcoplasmic reticulum, okay? X on the troponin, remove this tropomyosin, then these two see each other, and then binds on it, ATP is used, So ATP become ADP, and that released phosphate to provide the energy to make a power stroke, and then muscle, the myosin head move, and we have the muscle contraction. So this is the cycle of the power stroke. As I mentioned before, it's 4 steps. Step 1, 2, 3, 4. You have to have it tilted, attach, and swing, and release. So 4 steps. So you have first have to have, what's that? So this one is detached first. And okay, so that's this one here, the very first step. Step 1 is this one here. It's already ATP on it. So it's already, everything's ready, just waiting for. And then it has the ATP released to ADP and P. And so it's tilted. And when the calcium is available, it binds on it. When it binds on it, P is released, okay? And then ADP is released. When ADP released, it tilts. Now, that's the tricky part. When everything is released, I mean ADP and P is released, it's tilted, but it's not released. It's not attached to it yet. The way to make it attached is to provide an ATP, okay? ATP will have to it, and it attach. So the key here is this step. This step is important. This step is important in the way we will talk about. But now what you really need to remember is that there are 4 steps: tilt it, bind it, move it, and then release. Okay. This release needs a new ATP to it. Without new ATP, it won't release. That's very important. Without new ATP, it won't release. A lot of time that, okay, so why is that important? Because a dead person don't have the ATP. So the people who die, they don't have the ATP. This binding is not released. Muscle become rigid. Okay, that's why. No ATP, the myosin and the actin just love each other until the death. Okay, they are not leaving each other. They are binding on each other. So this one is a power stroke, cycles, 4 step. We mentioned earlier right here. Do we talk about that? No. All right. But you need to know what's so ATP released, breakdown to ADP plus P is the arm movements, arm tilted, and then arm moved, and then P is released when head binds to the active site, and throw away ADP power stroke. So when this time throw away ATP and throw away ADP power stroke, but now it's still attached. A new ATP is needed in order to make them separate. And the reason why is that important? Because that body, no ATP, no new ATP, so muscle will remain like rigid. That is the reason. That's why you see the rigid, like dead people. You don't see dead people, but you probably saw dead animal before. So this one is called a sliding filament. That we have in the beginning, we have I band, A band, H zone, and when they are relaxed, this I band is is appeared. When they contract together, everything will be filled by the thick filaments, and so I band will become shorter, and all things like sarcomere will become shorter. So here is we stimulate the muscle with an action potential. So there is two things. There is a timeline, right? So we have this nerve send signal to the muscle generate action potential. Action potential will allow calcium to go in. So here. Right here, right? Action potential will allow calcium to go in. So when action potential is very short period of time. Calcium go in, and then cause this contraction. This contraction will be much slower and longer for a longer time, because as long as calcium is there, muscle contract, right? So there will be two events, calcium and the contraction. Sorry, the action potential and the contraction. So the action potential is the stimulus, the contraction is right here. So we have first action potential, but after action potential, we have calcium going in and do this contraction. This contraction is called a twitch. It's called a twitch. Twitch is a single brief contraction of the muscle after an action potential. This twitch may be delayed for a longer time. If it's delayed for a longer time, it's called a slow twitched muscle. If it responds to it very quickly, it's called fast twitched muscle. And that twitch has to be above threshold. The stimulus has to be high enough to cause that twitch. And there's a latent period, that the delay of the stimulus and the contraction. And this latency defines whether the muscle is a slow twitched or fast twitched. As long as if the action potential, if this stimulus is higher than the threshold, it will trigger an action potential and cause a twitch. So this is like all or none. It's either contract or not. Type muscle, we have the slow twitched muscle and also fast twitch muscle. Usually muscle is a combination of all these. By doing training, we can convert one type to the other. And so for people doing like a sprint, that you need to have a large of contraction in a short period of time, you will be developed to a fast twitch muscle by training. If you are doing the training for the marathon, long distance running, then muscle will develop more slow twitched muscle. That you don't need to have a large force or quick response in the beginning, but you want it to prolong. You want to have a prolonged action of the process of the movement. So tension is the force. Twitch is the contraction of single muscle, but entire muscle organ has so many muscle fibers, right? So that muscle organ, like our biceps, that tension is a combination of all the twitch provided by all the muscles. Sometimes we only use some muscle, sometimes we use all the muscle, depending on how much tension we want to give provided by this muscle organ. So that tension depends on how many fibers participate, and the stimulation frequency, and also the number of cross bridge in each fibers. And also depends on length. So say we want to we want to generate that tension. If it's already like this one here, we cannot really generate any tension because it's just too short. If it's like this one, the tension has to coming from the longest. That tension will not be optimal either. The best tension is the the middle length. So that's right here. So if this muscle is already very long, like we extend it, that there is no much of this cross bridge with the myosin and actin, then they will not generate the tension large enough. If it's too short, it's already contract in a way that we cannot generate tension further. So the optimal is the middle one, optimal length. Great response is that the muscle contraction can be increased by, the tension can be increased by, if we want to push it larger force, we can use more muscle, or we can stimulate it, use our brain, right? Push it, like to provide more nerve excitation and higher frequency to excite it. Or we can just recruit more muscle to provide that force. So it's called graded response. So we can have a single twitch or multiple twitch to reach a large of the response. So recruitment motor unit is from the one motor unit from one motor neuron, and and we can also increase that tension by recruit more motor neurons into the force generation. So that's the recruitment, that each motor neuron from the spinal cord can have multiple muscle. So if we just need one single small movement, we can just excite one nerve and provide that tension. Each muscle will produce one twitch, and the 2-3 muscle will provide 2-3 twitches. And if we have more neurons, then more muscles are recruited, we provide a large tension. All right, again, that this contraction requires ATP energy. Require two things. One is ATP, the other one is calcium. Calcium can be reused. We're not going to break it apart. So calcium, we use it, we store it in the sarcoplasmic reticulum. But ATP, when we use it, we break it apart, then we need to have a new one. This new ATP is the reason why we eat, why we generate, why we have this metabolism that we learned just 2 days ago. So the ATP is needed to generate muscle contraction. One thing you need to know is that we use the ATP not just for the contraction. A lot of this energy is used to generate heat, okay? So when we contract, when we run, we not just run, we generate heat. We generate a lot of heat. And that's why you feel hot when you do exercise. So the source from the muscle use is in the beginning, they use the ATP, and the ATP very quickly used out. Then the next resource is the creatine phosphate. So that's also stored in the muscle. Creatine phosphate is like this one here. So here is the creatine phosphate. Creatine phosphate it contains one phosphate. So it can give that phosphate to ADP. ADP has diphosphate. So diphosphate got this phosphate to become triphosphate. And so we can regenerate. ATP is a metabolic like a byproduct from our muscle contraction. And so we can regenerate ATP from the ADP through this creatine phosphate. And after creatine phosphate give the phosphate to the ADP, creatine phosphate will form the creatine. So that's the like a second source to get the ATP, creatine phosphate. Following that, we use all the ATP, creatine phosphate, and what we can do, we would get energy from glucose, because in our muscle, we have the glycogen, right? The fuel we store in the muscle is glycogen. Glycogen is a polymer of glucose. So this one has a lot of glucose. Polymer of glucose. A lot of glucose. And when we need it, we basically just cut one out. And then we can use it to generate ATP. So glucose, the metabolism of the glucose is first is glycolysis, and then is the glycolysis generated pyruvate. Pyruvate will enter into the mitochondria. And the mitochondria will then go to the mitochondria, right? Yeah. Mitochondria. And then in the mitochondria, we have the oxidative phosphorylation to generate more ATP. To generate more ATP. And here, during that glycolysis, this glycolysis is an anaerobic exercise. This one generates 2 ATP. This one generates about 33 ATP. So in the beginning, we will have some glycolysis to generate ATP, and the glycolysis goes through this process. It's a little bit delayed. Then we have this aerobic exercise to generate more ATP. So we have the anaerobic first, that's the glycolysis, and then aerobic later. This is the oxidative phosphorylation through the mitochondria. And that will generate a lot more ATP. All right, so hormones also affect our muscle usage and development. Some muscle anabolic hormones are those who can make the muscle become larger. So these are typical one are the testosterone. This is the male sex hormone. So male and the females, the muscle size are genetically genetically different, are basically different. That's because that male hormone can stimulate muscle to generate more. The size of the muscle basically is the amount of the protein inside of the cell. So cell can be larger because of the containing protein is more. And the containing proteins containing not just protein, but also the organelles, include the actin and myosin. So these myofibrils. More myofibrils, your muscle will be larger and also will be more powerful. Growth hormone can also stimulate the muscle growth. Insulin, what's the insulin's job? Insulin will increase the glucose to be transported into the muscle and to boost the storage of the glycogen. So muscle will store more glycogen when insulin is there, and that will also make the muscle become larger. There are also proteins that can make the muscle become smaller, meaning that we will use some of this stored in the muscle. For example, cortisol. Cortisol is the one that your body have it early in the morning. So this one is the one that will utilize the glycogen stored in your muscle, and so the more cortisol, like the one who have an alert life, like very wake up early morning and have a busy day, they tend to grow thinner. That's because that cortisol, that kind of the pressure or alertness, will use the glycogen from the muscle to make the body to be more energized. Glucagon, very much similar, that glucagon usually released when our plasma glucose level is low. Glucagon is opposite to insulin. Glucagon is opposite to insulin. Insulin released when our blood glucose level is high, and the glucagon is released when our blood glucose level is low. So when our blood glucose level is low, glucagon will need to bring more glucose back to the blood. And the way they do it is that they will go to the muscle and get the glucose out of the muscle. And that will make the muscle become smaller. Thyroid hormone is a metabolic hormone. This one affects our basic metabolism, that our chemical reaction has a certain speed, and that certain speed can be increased by thyroid. So for people with thyroid, hyperthyroidism, for example, they will generate a lot of heat because their metabolic rate is faster, and they will be very alert. And with that metabolic rate increase will use a lot of energy. And where do we get the energy from? Hyperthyroid person will be hungry very fast. They will eat, and they will feel hot, and they lose the energy very quick. They lose the energy stored in the body very quickly. They either eat or they can get the glycogen from the muscle. Catecholamine, this is the sympathetic nerve neurotransmitter. This one includes the androgen, or we call it epinephrine, and that is the one that's triggered by our sympathetic, meaning that if we are in the fighting or flying mechanism, that our body is ready to fight. And when our body is ready to fight or run away, that will also use our energy stored in the muscle, because we need it right now. We store it during the peace time. Now we are in wartime. We need it. So the glycogen will be released from the muscle, and so muscle will become smaller. So those are the hormones related to the muscle. So that's it. I hope this has some help to your understanding of the muscle physiology. And stay safe and stay strong. See you next time.